Thank you for the wonderful introduction. Hi, hello, my name is Vukasin. I'll try to keep it short. I have 30 minutes, so you'll occasionally see QR codes on screen you can scan if you want to get more info. So first of all, who here knows how to program? Can we get, okay, cool, awesome. Who here has written Solidity? Who here enjoys working on large Solidity code bases? Amazing. So, who here knows how the EVM works? Cool. So the EVM is a stack machine. So it has transient memory, and it has a Merkle partition storage tree. So instructions get pushed onto it and then get executed. And a big misconception of how it works is that it's Turing complete, which is kind of true. In production, it's not. We have the block gas limits, so we cannot execute things perpetually. We know that they have an end. So Solidity has a big identity crisis. It tries to be a mix of Java, C++, and JavaScript. It's designed to be easy and pick up and learn, and this results in really poor UX, as Solidity programmers generally have to fight with the language and have to resort to using inline UL for a lot of things. So it's designed to be easy to pick up and learn, as I said. So it's great. This is great for general purpose programming languages, but Solidity is not a general purpose programming language. The EVM is not a general purpose architecture. In essence, it's a glorified SQL database we're manipulating, and Solidity should be complementing that. But yeah, due to the approach of being easy to pick up and learn, it's a very bad teacher, and it doesn't work because it's designed to be for settlements. So, as I've said, the EVM is inherently low level. So, Solidity should be complementing that by exposing users to low-level language features. But a lot of low-level language features that would make our lives easier are abstracted away. So, a great example of this is the type system. So, this disgusting code is used to extract data from the bytes. So, Solidity can only cast types of equal size or type. So what we have to do is we have to convert this to bytes 20 and then do our arithmetic by converting that to uint 160. Then back to bytes 20, bytes 4 to equal cast it, and then to uint 32. So this kind of shows that like it's way too low level to do an automatic cast, and it's way too high level to deal directly with bytes. So, who here knows how floating point numbers work? Okay. So, floating point numbers are used to approximate real numbers. So, and the most common implementation is IE754, where we have a significant, a base, and an exponent. And when we combine these three, we get an approximation of a number. So, they're more tightly packed around 0, and they're approximations, they're inaccurate. We are approximating them, so when we shouldn't be using them in applications where information accuracy is critical. And the EVM doesn't have them. So if I have an ARM laptop and you have an x86 desktop, there's a very good chance that my floating point number would be different from your floating point number. So that would cause a fork in a blockchain, which is something we absolutely do not want. And Solidity doesn't offer us a native alternative. And even though Viper does, Solidity doesn't. The excuse for this is that there is way too many implementations of decimal numbers. So yeah, we're kind of forced to use our own or use third-party libraries, which opens up to supply and chaser attack, and of course implementation bugs. So writing readable code is absolutely essential, especially for this field where we are dealing with money settlements. So proper formatting, naming, and code comments can give non-technical users an idea of what your code is doing, which is pretty important. And Solidity is becoming less and less readable. And I find that trend pretty concerning. Modifier, this is going to be a spicy one. So modifiers are used to amend the semantics of a function in a declarative way. So this is how they look like in practice. And this fragments code, and in my opinion, is terrible for readability. So let's take a look at the following. On the left, we have something called a board that can only be called by the seller. So we do this via modifiers here, and then we do the same thing here. I don't know about you, but this is much more readable, this one-line solution, than whatever this is. And now consider that most modifiers are used like this, where they're imported from some random place and used like this. Yes, the naming is kind of telling what it's supposed to do, but it's still it's not very transparent. And most uses for modifiers are stuff like only seller or reentrancy guards, where we can use and should use things like check effects interactions. So, or can be done in a single line of code, like this. So it just fragments everything. This is also going to be a spicy one. So inline UL. So yes, using UL does save gas, but there's a hidden cost. It makes your code completely unreadable. So this here is a snippet from OpenSea. It's used to transfer ERC20 tokens. So yeah, I generally find UL fine for stuff like arithmetic, but using it for large parts of the business logic shouldn't be done. It makes it hard to audit, read. And yeah, as Nikolai Mushegan said, complexity is the enemy of security, and we should be avoiding complexity. So user-defined operators, they are a relatively new feature. They were introduced in 0.10.19. And they're designed to make user-defined types easier to work with. So in addition to having the same problems as modifiers, you also have the problem of not knowing at a glance if you are executing a function. So we've seen from other languages how people get carried away with stuff like this. And yeah, it's not something that should be happening in a smart contract programming language that should be readable. And to properly overload an operator, you must understand transitivity, commutativity, and distributivity. And maybe you do know how all of this works, but lots of people don't. I certainly don't. So yeah, but there are some cases where they do have legitimate use cases, like custom decimal types, where it's very hard to get multiplication, subtraction, and all these kinds of stuff hard to get wrong. And the Solidity team is aware of the complexity, but in the blog post, when 0.10.19 was released, they argue that it reduces complexity and increases readability. And this is the example they gave, which is a bit cherry-picked, but yeah, sure, let's go with that. Delegate call, so it creates a new subcontext as if calling itself, but with the code of the call contract. And what this essentially means is that we have a proxy contract that delegate calls into a logic contract. And what this allows us to do is to have proxies that have business logic here. So it costs to deploy a proxy contract is relatively cheap, and then you can use the storage of this one with the logic of this one. And it makes things like upgradable contracts diamonds, if you're masochistic, and abstraction, account abstraction, kinda, are possible due to it. So the EVM has storage slots that are 32 bytes long. So we have a unit 256. This is the alias for that. This is one slot. We have an address, it's 20 bytes, and some bools, which are packed into one slot. And then we have 2 additional slots that are taken up by these things. So it has a really bad reputation because it's very easy to blow yourself up if you use it incorrectly. If you get storage slots wrong between the proxy and logic contracts, it's very easy to get undefined behavior. And Solidity, because of this, Solidity has it as a low-level call. And there's no way to check if you are doing storage loss properly. So at Rainshower, we deal with a lot of proxies and we delegate call into large business logic contracts. And this is something I would really like to see fixed or like improved on and added, as it's very hard to keep track of all these things. So Sol-C is the reference compiler for Solidity, and the lower level workings of it aren't documented very well. So if I do make some mistake somewhere, you have my Twitter, please scream at me. So yeah, let's go. It's very bad at optimizing code. Solidity code is consistently worse than inline YUL. And this is really bad because we have modern compilers that almost always produce code that are better than a human could ever write. Like if you take a look at GCC or Clang, they will always produce better code because they have 20 or so years of research put into them. They have all the knowledge of an instruction set you're developing for, and the human simply cannot do that. And here we see that Solidity is up to 50% worse than using it with YUL. It's really bad. Even if you take hidden checks, like checking if ether is sent to something that shouldn't be sent and things like that, that's still not an excuse. There should be at least parity between the two. A very good example of this is the free memory pointer. So Solidity needs a free memory pointer due to having dynamic size types. So this is how that looks like in EVM opcodes. And you can scan this to learn more about it. So here we see bytes is a dynamic type. We do not know its size in advance. It can be anything. And it makes sense to have a free memory pointer here. But if you take a look at this, bytes to static, we know the exactly how much memory we need in advance. And the free memory pointer is still there. So this is a really good example of how Sol-C is unaware of what your code actually does. Via IR, so it's designed to optimize your code, and which basically means in the Sol-C context of it to modify it so that it fails most quickly and spectacularly. So what do I mean by that? It's a feature of the compiler that uses YUL, an intermittent representation of it, to optimize it, hopefully. And the plan is to replace it with legacy bytecode generation by the end of the year. And if you used VIR, who has used VIR before? Okay, so you know how slow it is. Yeah. And in addition to being really slow, it contains semantic changes compared to legacy bytecode generation, which means that the code you generate without VIR can produce different outputs to code you generate with it. This is completely unacceptable in a smart contract programming language. Yes, there are technical reasons for why it's like this, but at the very least, I expect something like a pragma that we put Solidity version, but like for VIR. And it is largely undocumented. Most of my research for what VIR is and does came from reading GitHub issues, which is kind of funny. This is a very notorious bug with VIR that was fixed relatively recently, where IR-based compilation increased context size when an internal function is called many times. So what that basically means is that if you call an internal function multiple times, it will inline it, and your code will have be up to like 3 times larger than it should be. So yeah, this is a really funny anecdote. If you wanna read that, you can scan the QR code. So, to conclude, Solidity has numerous design flaws and limitations that make it less than pleasant to work with. Its mixture of high and low level features make it pretty awkward and cumbersome to use, and the lack of compiler optimizations force the programmers to write inline assembly to not have to deal with the compiler. And I think that one hurts the most, because if you have to use inline assembly, you fail at designing a programming language. And give Viper a go. Viper is Viper is great. It's not doesn't have parity with Solidity. It doesn't have dynamic types. It doesn't have infinite loops. But there are some trade-offs that they make to have it be a compelling option. So if there's one thing I want you all to take away from this, is that maybe we need to rethink about how we are designing and writing smart contracts. So thank you. If you have any questions, DM me on Twitter or ask me here, or if you want the slides, shoot me a DM. Here's my Twitter. And yeah, thank you.